Imagine hurtling down a vast, open highway at a steady 65 miles per hour. The road ahead unfurls like a ribbon, and every second, new challenges and opportunities race into view. In a world where human drivers rely on instinct, intuition, and split second judgment, autonomous vehicles must harness the power of advanced computation to safely navigate. Behind what seems like a smooth and effortless journey is a marvel of modern engineering, a sophisticated interplay of perception, prediction, planning, and control. Today, we embark on an immersive exploration of how these vehicles operate, revealing the layers of artificial intelligence that transform raw sensor data into decisive, real-time actions on the road. The challenge of enabling a car to drive itself is a monumental one. Consider the simple act of driving. A human sees the world, processes that information, anticipates what might happen next, and then takes action. For a machine, each of these steps translates into a series of complex problems that must be solved in fractions of a second. Understanding the environment, forecasting the evolution of that environment, deciding on the most prudent maneuver, and executing that decision precisely, all of these tasks occur in an endlessly repeating cycle. This cycle, often completed dozens of times per second, is at the heart of autonomous driving. At the core of this challenge lies a crucial question: how does an autonomous vehicle interpret the world without a human at the helm? The answer is found in a layered intelligence system built through the union of advanced sensors, neural networks, and control algorithms. This technological marvel operates on the principle that a self-driving car is not guided by a single algorithm, but by an entire ecosystem of interconnected systems working in harmony to perceive, predict, plan, and control every maneuver. When a vehicle glides down the highway, every element around it is continuously assessed. Sensors, including high-resolution cameras and other detection devices, gather an immense amount of data from the surrounding environment. This raw, unstructured data composed of millions of pixels is transformed into a dynamic three-dimensional representation of the world. It is here that neural networks come into play. Deep convolutional neural networks process every frame, discerning edges, shapes, and objects by comparing patterns across multiple layers. In effect, these networks upgrade simple pixels into a rich, detailed map that is capable of distinguishing between a merging truck, a swift motorcycle, or a subtle change in lane markings. The process of perception, however, is only the first step. Sensing the environment is akin to having a high-definition photograph of the moment, but driving demands foresight. Once the vehicle has constructed this digital map, it must predict how the scene will evolve in the blink of an eye. Autonomous systems apply behavior modeling algorithms and probabilistic decision-making to forecast the future trajectories of every object in its vicinity. For instance, when a car signals an intent to change lanes, the system calculates several potential outcomes. It may assess that there is a 70% probability that the car will complete a smooth merge, a 20% chance it might decelerate, and a 10% possibility that it could accelerate unexpectedly. This forecasting is central to ensuring the vehicle can adapt to an environment that is anything but static. Planning is the subsequent layer of intelligence, a domain where every possible path is scrutinized. Within a matter of milliseconds, the vehicle's planning module generates numerous potential trajectories for itself. Each path is evaluated against a wide array of factors: adherence to traffic laws, the predicted behavior of surrounding vehicles, the physical dynamics of the car, and even the comfort of its hypothetical passengers. The interplay of these factors, all balanced within tight safety margins, leads the system to select not just a single maneuver, but a fluid strategy that continuously updates as circumstances change. In the world of autonomous driving, planning is a perpetual balancing act between caution and efficiency, where the objective is to choose the safest, most reliable path among many options. Translating these decisions into action falls to the domain of control. Once a trajectory is determined, the vehicle relies on precise feedback loops and conventional control principles to execute the maneuver. Controllers within the car make rapid micro-adjustments to steering, throttle, and braking. This orchestration is based on the physical laws that govern motion, ensuring that the chosen path is followed with remarkable fidelity. In an environment where errors measured in milliseconds can have profound consequences, the precision of control systems is nothing short of critical. But there is more to this intricate system than just real-time decision-making. The intelligence that powers autonomous vehicles is nurtured through an intensive training process. Neural networks are not born knowing how to drive. They are educated using billions of miles of data collected from vehicles navigating real-world conditions. In vast data centers equipped with thousands of specialized processors, these networks are exposed to countless scenarios. Every image captured by the car's sensors is meticulously labeled, identifying lane boundaries, traffic signals, pedestrians, and even rare and unpredictable events. This rigorous training adjusts millions, if not billions, of parameters within the network, constantly refining its ability to interpret the world accurately. On board the vehicle, dedicated hardware takes on the monumental task of executing these highly complex computations in real time. A specialized self-driving computer engineered for speed and reliability processes streams of data and runs advanced neural networks continuously. These systems are built with redundancy in mind. Multiple processing units work in concert, cross-checking one another's outputs to guard against potential failures. This commitment to reliability ensures that the system remains robust even in the face of unforeseen challenges. It is a testament to engineering ingenuity, where every component is meticulously optimized for both performance and safety. Yet even the most advanced systems face hurdles in an unpredictable world. Edge cases, the rare, unexpected scenarios that challenge the system's limits, are among the greatest obstacles for autonomous vehicles. Imagine a sudden construction zone, debris scattered across a well-traveled road, or the ambiguous silhouette of an object at dusk. These are not everyday occurrences, yet they demand precise handling to maintain safety. Engineers tackle these challenges by continuously feeding real-world data back into the training process. Through simulation and iterative testing, the system learns to accommodate the unusual and refine its performance, reducing risks incrementally with every update. Safety validation is another critical pillar of the autonomous journey. Before any software update is deployed to a fleet of vehicles, it undergoes extensive simulation testing. Virtual environments recreate a myriad of potentially dangerous scenarios, from congested urban settings to isolated rural roads under adverse weather conditions. By analyzing performance metrics, such as disengagement rates and collision probability estimates, engineers can ensure that every update delivers a statistically significant improvement in safety. This rigorous process provides a constant feedback loop where extensive real-world driving data informs incremental advancements, steadily closing the gap between machine calculations and the unpredictable nature of the road. Among the debates that continue to animate the field of autonomous driving is the challenge of sensor selection. Some engineers advocate for the use of LiDAR, a technology that employs laser pulses to determine distances with extraordinary accuracy. Others favor vision-centric systems that rely predominantly on cameras, complemented by other sensory inputs. Each approach carries its own advantages and limitations. LiDAR offers precise depth perception, but at often higher costs and complexity. Vision-dominant systems, on the other hand, can draw on the richness of image data to build comprehensive three-dimensional maps. Regardless of the chosen sensor suite, the underlying challenge remains consistent: converting streams of raw data into reliable, safe actions in a world filled with uncertainty. There is also the question of human versus machine in the realm of driving. Humans bring intuition, experience, and an intrinsic understanding of context to the table, qualities that are difficult to encapsulate in lines of code. Yet, human drivers are prone to distractions, fatigue, and emotional influences. Autonomous systems, by contrast, offer a form of consistency and precision that is anchored in relentless computation. They process data without distraction and operate tirelessly, even as they contend with the inherent difficulty of managing rare events that humans might naturally navigate with intuition. The path forward is marked by continuous innovation. With every passing day, hardware becomes more powerful, software more refined, and training datasets expand to include even more complex real-world scenarios. Autonomous systems are not static. They evolve with each update, becoming smarter, faster, and safer. The improvements in sensor quality, computational efficiency, and algorithmic accuracy are driving us ever closer to a future where autonomous vehicles seamlessly integrate into our daily lives, where the invisible intelligence behind the wheel not only navigates but also learns and adapts from every mile traveled. The journey to fully autonomous driving is, fundamentally, a tale of relentless engineering and innovation. It is about building an ecosystem where sensors, neural networks, and control mechanisms function in perfect harmony. As we delve deeper into the technical intricacies of these systems, we witness a symphony of algorithms and hardware working together to solve one of the most challenging puzzles of our time. Every component plays an indispensable role in ensuring that the vehicle not only navigates but does so with an unwavering commitment to safety. From the high-resolution cameras that capture fleeting moments of reality, to the onboard computers that transform data into motion. Reflect on the idea that while a human driver processes the world through choices tinted by experience and emotion, an autonomous vehicle relies solely on cold, calculated data. Here, ingenuity is not measured by intuition, but by the capacity to crunch billions of data points at a staggering pace. It is a world where decisions are weighed in probabilities, a 70% chance of one outcome, a 20% chance of another. This probabilistic approach is what lends the system its predictive power, allowing it to prepare for multiple eventualities simultaneously. In the operation of these vehicles, every fraction of a second counts. As a car barrels down the highway, it covers nearly 30 meters every second. If the vehicle's computational system ever lags, even by a mere moment, the consequences could be disastrous. This stark reality underpins the immense pressure to design systems that perform reliably and without delay. It also explains why redundancy, having multiple layers of checks and balances built into every system, is not merely an option, but a necessity. Every sensor reading, every calculation, every control adjustment takes place under the vigilant watch of engineered safeguards meant to protect both passengers and other road users. Looking closer at the sensors themselves, the perception module is nothing short of a technological marvel. High-resolution cameras, strategically placed around the vehicle, collaboratively capture a panorama of the environment. These images form the raw material from which the vehicle constructs its digital view of the world. At the heart of this transformation are neural networks which function much like the human visual cortex, interpreting shapes, colors, depths, and motions. The iterative process begins with simple feature detection and evolves into a detailed, layered representation of surroundings. Each detected object, be it a pedestrian edging near the curb or a car merging from a side street, is not only recognized but precisely located in three-dimensional space. This information is continuously updated, ensuring that the vehicle maintains an accurate and current understanding of its dynamic environment. Once the scene is understood, the vehicle must shift from a static representation to a dynamic forecast of the future. Prediction systems, employing behavioral models, estimate how various objects are likely to move. They calculate multiple trajectories, each weighted by likelihood, and thereby construct a probabilistic map of the near future. This isn't about certainty, it's about preparedness. The vehicle's decision-making process is rooted in understanding that the future is not fixed, and that safety depends on acknowledging uncertainty. With each scenario, the system assesses potential risks and reevaluates its strategy in real time, an essential feature in a world where a split-second decision can make all the difference. Planning, the next critical phase, is where theory meets practice. After constructing a current and anticipated map of its environment, the vehicle's planning module generates potential paths. These paths are not arbitrary. They are built upon strict parameters that honor the laws of physics, traffic regulations, and safety protocols. Optimization algorithms come into play, meticulously scoring each potential route based on its predicted efficacy and safety. The selected trajectory is one that not only promises a smooth drive, but also incorporates buffers for unexpected developments. In essence, planning is the art of choosing the path that minimizes risk while maximizing safety, a balancing act executed with mathematical precision and engineering foresight. Once a path has been chosen, the final stage of this intricate process control takes over. In control, abstract plans become tangible actions. Through rapid feedback loops, the control module adjusts steering, throttle, and braking in real time, ensuring that the car adheres to its designated path. This phase is deeply rooted in fundamental principles of physics, where even the smallest adjustment plays a critical role in maintaining stability and safety. It is here that the meticulous planning is translated into the reality of motion, ensuring that every twist, turn, and change in speed is executed flawlessly. Every aspect of this integrated system is continuously refined through a robust training regimen. Autonomous systems benefit from the cumulative wisdom of billions of miles of driving data. This data, gathered from vehicles navigating diverse conditions, provides a vast reservoir of real-world scenarios to learn from. In sophisticated data centers, neural networks are trained under rigorous conditions, fine-tuning millions, even billions of parameters to minimize errors. The result is a digital brain that continually adapts, learns, and improves, becoming better equipped to handle both routine circumstances and rare, critical events. This feedback loop of data collection, training, and real-world application forms the backbone of innovation in autonomous driving. In this journey, onboard hardware plays a pivotal role. A specialized computational unit, engineered for self-driving applications, manages the enormous task of running these calculations in real time. With precision-engineered processing units and built-in redundancies, these systems ensure that the information flow and decision-making processes occur without interruption or error. It is a prime example of how cutting-edge hardware and sophisticated software combine to form a reliable, high-performance system that is capable of interpreting the world and reacting to it with the urgency of a human reflex. Despite these advances, engineers remain acutely aware that the road to autonomous driving is fraught with challenges. Edge cases, those infrequent, unpredictable scenarios, demand constant vigilance and adaptation. Whether it is an unexpected obstacle, unusual lighting conditions, or a transient flaw in sensor data, every anomaly is scrutinized and used as an opportunity to further refine the system. Extensive simulation programs, along with rigorous validation protocols, ensure that even the rarest events are anticipated and managed. Perhaps the most striking aspect of this journey is how a seemingly simple act of driving is transformed into a complex dance of algorithms and computations. The invisible driver, the amalgamation of neural networks, planning engines, and precision control loops, is not a singular entity, but the result of an immense collaborative process. It is a testament to human ingenuity, a reflection of decades of research, experimentation, and relentless pursuit of perfection. It transforms what once was a basic mechanical activity into a sophisticated interplay of behavior modeling and physics, data processing and anticipatory safety measures, where every decision matters and every millisecond counts. As we stand on the brink of this automotive revolution, it becomes clear that the future is not merely about vehicles that drive themselves. It is about a transformative shift in how we understand motion, safety, and technology. Advances in sensor technology, the ever-growing power of AI algorithms, and the continuous influx of real-world data converge to create a system that learns, adapts, and evolves. This is a future where our roads become arenas of intelligent design, where the interplay between technology and the environment reaches new heights of precision and reliability. Today, as we witness a car glide effortlessly through traffic without human intervention, we are not seeing a machine merely following a preset program. We are witnessing a culmination of countless hours of design, testing, and innovation. A harmonious blend of cutting-edge hardware, refined algorithms, and a deep understanding of both physics and human behavior. It reminds us that while the technology driving these vehicles is profoundly advanced, it is also a creation born of trial, error, and the ceaseless quest for improvement. In reflecting on this journey, one cannot help but feel awe at the complexity embedded in what might seem like a simple drive. Every sensor that scans the horizon, every calculation that weighs probabilities, every tiny adjustment that steers the vehicle safely along its path, all of these components work together to achieve what was once thought impossible, a fully autonomous system that can interpret reality and react with precision. It is a milestone in the evolution of transportation, marking a transition from human-centric intuition to machine-learned expertise. As we look forward, the challenges remain significant but not insurmountable. Developers and engineers continue to push the boundaries, improving neural networks, refining control strategies, and expanding the data that informs each decision. This ongoing iterative process ensures that, with every update and every resolved edge case, the system becomes more reliable, more intelligent, and ultimately safer. It is the spirit of innovation driven by the determination to create a future where autonomous vehicles are not only a technological marvel, but also a standard bearer for safety and efficiency on our roads. Our exploration today reveals that behind every self-driving car is an intricate web of computations, sensors, and algorithms working tirelessly to ensure that the vehicle navigates the unpredictable and ever-changing world. The autonomous vehicle is not merely an automated machine. It is a living, evolving system that learns from experience and adapts to new challenges. It represents one of the most ambitious endeavors in modern engineering, teaching a machine the art and science of driving. In conclusion, the journey of autonomous driving is as much about understanding our environment as it is about reimagining the very act of movement. Every mile traversed by these vehicles stands as a testament to human ingenuity and the relentless pursuit of perfection. From the initial detection of a simple shape on a busy highway to the sophisticated planning and control that enable safe navigation, the invisible driver inside these vehicles is continuously learning, refining, and striving for excellence. As we continue to innovate and push the limits of technology, the promise of safer, more efficient roads becomes ever more tangible. Remember that each advance, each refinement in these complex systems, brings us one step closer to a future where the harmony of artificial intelligence and human aspiration drives us safely forward. Discover our journey now.